part C of lecture 24. I just wanted to walk you through the code that solves this problem. In part B, I solved this problem, but with by hand, kind of. I sketched the solution. So we have two elements. We have the material properties. There's no traction, so traction of 0. So traction boundary conditions of nodes 3 and 4, but traction equals 0. Essential boundary conditions for nodes 1 and 2, fixed displacements, and a body force, which is 0 in x and then gravity times thickness times density in y, and constant throughout the body. Here's the mesh information, again the essential boundary conditions, no information given about traction boundary condition, but that just means that the other nodes have 0 traction. To solve the problem the same way as usual, you would have to get the stiffness matrix for each element. Because these are linear triangle elements, all you need to be able to calculate is the B matrix, which is just dependent on the nodal coordinates of the triangle, the D matrix, which has the material properties, and then because the B matrix is constant and the D matrix is constant, the stiffness matrix is just area times BdB. So typically you would have to do the integral, but in this case, because it's constant, just multiply by the area. So hopefully all of those concepts are clear. And this just, if you carry out the multiplication with Python, for example, this is a 3x6 matrix, this is a 3x3 matrix. If you do this multiplication, you get a 6x6 matrix. And the big question is, how do you assemble the 6x6 matrix into the global stiffness matrix? In this case, there's 4 nodes. So the global stiffness matrix is actually 8x8. And that's gonna be the trickiest part of the code. I'm gonna show you the coding a little bit, but I'm just trying to make the case for basically this part should look very, very familiar to what you've done before. This part is similar to what we did for the 2D trusses. So here, when we do the assembly, we typically put the global node numbers in the columns and the rows. Now in this case, every node has x and y degrees of freedom. So here I have, for example, global node numbers 1, 2, and 4, but each node has x and y. So 1x, 1y, 2x, 2y, 4x, 4y. But this is not how you access a matrix or an array in Python or MATLAB. You cannot say, oh, give me the 1x coordinate or the 1y coordinate. So instead, you need the actual index of the array, of the matrix. So what you can see here is, for example, that if you look at the global stiffness matrix, where you have all known numbers, so 1, 2, 3, 4, and 1x, 1y, 2x, 2y, you see that 1x corresponds to entry 1, 1y corresponds to entry 2, 2x corresponds to entry 3, and so forth. So you can see that node 1 goes to entries 1 and 2, node 2 goes to entries 3 and 4, and so on. And these are the actual values that you need to access. So not 1x, 1y, 2x, 2y, but these values. And there's a formula that you can use to calculate them. It's just twice the number of the node, and then either plus 1 or minus 1, depending on whether you want the x or the y coordinate. So I think that's the key thing for the assembly. So let me show you the code. So this is the code that I uploaded to Blackboard for lecture 24. The gradients of the shape functions for the linear triangle, these are standard. I just copied them from the textbook. I don't even have the shape functions for the triangle because I don't use them in this case. Otherwise, you would also need def n1, and then dependent on all the coordinates of the triangle and x and y. So you would have x, y, and then all the coordinates, and then you would do something, some function. You would do, I don't remember the actual shape functions, but you can look them up in the book. So I'm just gonna comment this one, but I actually don't need the shape functions for this case, and then an area. Now here for the problem, we have a mesh which is defined by 4 nodes, 2 elements. These are the nodal coordinates. This is the element connectivity. So the first element is made out of nodes 0, 1, 3. Note that I adjusted the numbering, and this is, the difference between MATLAB and Python. So here I have, or Abacus, the node numbering from 1, but for Python, the node numbering has to be from 0, so I just subtracted 1. This is the second element. These are the material properties and the loads. Initializing the stiffness matrix and force vector. The stiffness matrix is 2 times the number of nodes times 2 times the number of nodes. The force vector is 2 times the number of nodes. As usual, I have a loop over the elements. So for I in range number of elements, for every element, I have 3 nodes. And now there's a reason why I do this. Typically, I do this. So typically what I do is n1 equals elements I, 0, n2 equals elements I, 1, and n3 equals elements I, 2. So that's what I would do normally. But instead what I'm doing is I'm putting n1, n2, and n3 in an array. So you can see that basically equivalent to nodes equal n1, n2, and n3. So all of this is basically the same as this line right here. And note that, so the nodes array has the global node numbers of element I. Right? and I'll come back to why do I put them in an array. Then given that I know the global node numbers, then I can use those global node numbers to access the node X array and get the corresponding X and Y coordinates. Then to build the stiffness matrix, the B matrix just copied directly from the book. All you need is the coordinates of the triangle and the area of the triangle. The D matrix, again, just copied from the book. This is just dependent on the material properties. The stiffness matrix, no need to do an integral, just area times B transpose times D times B. And this gives you a 6 by 6 matrix. And I'm printing it. I'm multiplying by 3 just so that the printing looks, like whole numbers. Because it's some multiple, it's like, if you just print the stiffness matrix, it will have a lot of decimals. And now this is the key thing. I need to assemble this KE matrix into the global K matrix, right? So I need to do this mapping right here. I need to take these parts of the stiffness matrix and put them into the global stiffness matrix. And why am I doing this in these loops? The reason for doing it in these loops is that typically I would have, what I've done in the past is I have, for example, for the heat transfer problem, I would have K n1 n1 plus equals KE 0 0, right? And then K n1 n2 plus equals KE 0 1, K n1 n3 plus equals KE 0 2, and so on, right? So this is what I would do for the heat transfer problem. Now in the heat transfer problem, the matrix is just 3 by 3. The KE matrix is 3 by 3, so I only need to do this 9 times. Now in this case, the KE matrix is a 6 by 6 matrix. So in reality, entry 0 0 corresponds to n1x n1x. Entry 0 1 corresponds to n1x n1y. Entry 0 2 corresponds to n1x and 2x. Let me just do a couple more. So the next one, so 0 3 will be this. Then and 3x will be 0, 4, and finally and 3y will be 0, 5. And this is just the first row. So I need to repeat this 6 times, one for each of these. So the next row would start with n1y, and this will be 1, 0. And I mean, probably you can imagine how the rest goes. So now everything will have n1y, and then I will just be changing the second entry, right? So I would need to write out 36 lines, and I don't want to do that. I actually would rather do it in a loop. Let me delete this. This is not really important. So actually this looks as simple as these four loops. The one thing that I also haven't said here is actually the entries should be n1x and n1y and 2x and 2y and so on. So right now I only have n1, n2, and n3, which are inside of this nodes array. But I need to go from, so the first question is, how do I go from n1 to n1x and n1y? And this is what I was trying to explain. I don't know if I did a good job or not, but that, 1x, so 1 goes to 1 and 2. So from the global known number, you can get the two values. 2 goes to 3 and 4. 3 goes to 5 and 6, and so on. In this case, because the ordering is from 0, n1 goes to, so if I know n1, then n1x is going to be n1 times 2 plus 0, and n1y will be n1 times 2 plus 1. So given n1, I can get the corresponding x and y, just multiply by 2 and either add 0 or 1. And then for n2 is going to be the same. So from n2, I need to get to n2x. That's just going to be n2 times 2 plus 0. And from n2 to n2y is going to be n2 plus 2, n2 times 2 plus 1. And same for n3. So I would need to write out, maybe before here, I would need to write out all of this. So I would need to say, n1x equals this, and then n1y, and so on, right? So I would first have to define all these 6 different mappings, and there are 4 here, but I'm missing n3. And then I would have to write out these 36 lines of code, and I don't want to do that. So instead, believe me that these four loops are doing exactly that. So here I'm looping ni goes from 0, 1, 2. Then coordinate I is basically 0 or 1. Then this is again 0, 1, or 2. And then this is again 0 or 1. So you can probably see that here, this number is gonna, because of the for loops, so first this is gonna be 0, right? And while this stays 0, because ni is gonna be 0, right? This is gonna be 0. And then because these are inside of that for loop, so for ni equals 0 and core I equals 0, this will go through 0, 1, 2, 3, 4, 5. Then next time this will be 1, right? This is still 0. So now this will be 1, and this will go 0 through 5. And then for the next iteration, now ni will change. So this will be 2, and this will go from 0 to 5, and so on. So you can see that these 2 terms right here are basically looping through the 36 entries of KE. And then the corresponding mapping, so if this is the local known number times the x or y times the coordinate, the corresponding mapping is nodes ni times 2 plus core I. And hopefully that is clear. And that's why I created this nodes vector at the beginning. So that instead of calling directly n1, I call nodes ni. And that automatically will give me n1, n2, or n3 as ni loops from 0 to 3. And this one, same. Yeah, so that's I think that's the trickiest part of the code. And if you have questions, let me know. You can always go and do the 36 lines of code if you want to. There's nothing wrong with that. This is just a lot more compressed. Now for the force vector, in this case, the force vector is a constant. So I gave you this formula for the force vector. It's in the slides as well. So it's a 6 by 1 vector, and it depends on the value of b at different nodes. In this case, the b are all constant. All the bx are 0, all the bys are the same. So if you work out the algebra, then it just simplifies to having, the entries 0, 2, and 4 are 0, and the entries 1, 3, and 5 are just a over 3 times rho hg. And then the assembly, I am doing something very similar to what I was doing for the stiffness, but in this case, I only need to loop through the rows of the vector. So it's kind of like just this half, so I only need these 2 loops. And that's it. I'm just printing them out for visual purposes. Finally, partition and solving is the same as always. Need the number of essential boundary conditions. Remember that even though there's 2 nodes that are fixed, they are fixed in x and y, so I have actually 4 essential boundary conditions. And then that's it. I mean, the rest, this is pretty much the same as always. You partition the stiffness matrix, you partition the force vector, create the vector with the essential boundary conditions, in this case all zeros, solve. So the rest should be very, very similar to what you have seen in the past.